you just calculate step by step. First integration in G, and the second integration in Y, the third last integration in X. Then finally you get the result, it is 0. I think I don't give more detail because in this step this is very easy to calculate. Okay. If you want, I can give this one more detailed step. So this is integration from -1 to 1, intervals from -2 to 2. And here in integration in dz, then you can see if it's x, y, g, plus here 1/2 x g power 2 plus 1/2 y g power 2. It takes from -3 to 3 dy and dx. And similarly, you calculate this integration from for y, and then for x, and finally you get the result is 0. Okay. Question 1b. Integration in d x y g e power minus x power 2 minus y power 2 dv. So look at the reason d. D is similarly d is a box, and you get to go from 0 to square root of 2. To go from 0 to square root of 4, to go from 0 to 1, x, y, g, e minus x power 2 plus y power 2 dz dy dx. Remember the order of the integration, the triple integration. And this, finally, we get the result 3/64. Quite simple. Problem number 2. Here, problem number 2 says that here the triple integral to find the volume of the following solid. Okay, so you can, if you want, you can use mapper to plot the graph of the solid. Okay. Now for question A, the solid in the first octant are bounded by the plane, here this plane, and the coordinate plane. So therefore, you can see this look like this. Yeah, this is exactly the solid. Okay, solid. All right. So here this is x, y, g. This one, it is a 2x plus 3y, 6g into 12. So now the volume V equal to integral on D is 1. The our function is now 1 dV. Okay, so we get this is the volume of the region D. And now from here you can see that this is equal to this is x. So when z and y equal to 0 and x is equal to 6. Okay. Similarly here is 4 and here is 2. Therefore 0 here. Therefore you can see that now first you take the integral in x from 0 to 6. Okay, from 0 to 6. When it's on the plane OXY, this line is 2x plus 3y equal to 12. Therefore, y from 0 to 4 minus 2x over 3. Understand? So on OXY. Over here. This line become to this. Okay. So in this reason that our 6, then you access to this reason and you meet from 0 to 6, and you will meet the line y equal to 0, and then this is line is 4 minus 2x over 3. Okay, so what happened for z? For z, you go from you access this solid from OXY, and then you get 0 first. Okay, the plane 0 first, 0 equivalent to OXY, plane OXY. And then you will every point and then you will meet this plane. So here is this exactly 2 minus x over 3 minus y over 2. Okay, so here is this 1 times dz dy and dx. Okay, so from here then you obtain this integration from 0 to 6, 0 to 4 minus 2x over 3. Now dz 1 dz becomes 2z. Takes the value from 0 to 2 minus x 3 1 2 dy dx. And once again, you calculate the integration in y and then in x, and finally you get the results 8. to get this value. Question B. Any question? Question B, when you draw the unit, it looks like this. So the unit is look like this. Okay. So this point is 0. And this point is 0, pi, 0. If someone want to ask question, question 1B. Yeah. What exactly is your question? You want to understand from where, which steps? Hello? Remember, because we will take the integration in G last. Therefore, first we always consider the integration in the plane our xy first. So our xy, look at here, when z equal to 0, and then the reason here, this exactly this look like this. Okay, it look like this. So now you access this reason for all value x from 0 to 6. And then you can see that when you go by this direction, and you always, when you access this reason, you go by this direction. And then first you meet this night equal to 0. Okay, and then
Teacher,
what?
is asking for question 1B.
Sorry, and then, because of internet, therefore I cannot hear the question clearly.
He is asking for the question 1B, not 2A.
Okay, okay, 1B. Sorry, 1B. Okay, yeah. So for the first problem, it's very easy because the reason D is a box. The box is very easy. For question 2A, the reason D is now is sonnet. Okay, sonnet is not a box. Therefore, it's a little bit complicated. Therefore, now it's okay. Question 1B is okay.
Teacher, can you go step by step of question 1B, because I don't know how to get the answer like that. Yeah.
Okay. So this one is integration from 0 to 6. Integration from 0 to 4 minus the 2x over 3. Okay, so actually I take the pens. Okay. One B, right? Okay, so now sorry, I forgot that there's the 2A's. So this is the 1/2, right? Integration from 0 to square root 2. Integration from 0 to square root 4. And here is this x, y, e power minus x power 2 minus y power 2 dy and dx, right? Why we have a 1/2? Because this is a 1/2 z power 2. You take the value from 0 to 1 and then you get this 1/2 here, right? Understand? Then now 1/2 to go from 0 to square root 2. And here this one is the x e power minus x power 2 minus 1/2 e power minus y power 2. This value from 0 to square root. What? Okay, sorry, let's see. Maybe when I type, and maybe this is, sorry. This is yes. Look, it's similarly to these problems when when typing, and this is there's some typos here. Okay, it should be log 2 and log 4. It doesn't matter. Maybe my results and your results is the difference because of this. Okay, understand? But if you yeah, when I check your solution, then if you calculate the steps correct, okay. So however, it's just different this point, and then it's okay. It doesn't matter. Okay, sorry. Right. So question 2A, do you understand? remember in 3 dimensions, and then you access from 3 direction, from 3 direction, from here, and then you can see if you access this region by in plane O X Y, and then you first you meet 0, and from 0 to 6 every point on this interval, and then you get 0 first and exist this 9, and now for Z you access from this direction, and you always exist. You always, every point, you always exist this plane. Therefore, that's why Z from 0 to this. Okay. Now for question 2B. Question 2B, look at here, and then you can see similarly have a integration. We have a B. So B equal to integration ups. D1 dV. So this is the integration from 0 to pi, integration from x to pi. So look at here, this is maybe I draw this is better. Yeah, this is like this. This line is y equal to x. Therefore, that's why you have x from y from x to pi, and z from 0 to y 1 dz dy and dx. So this exactly is equal to finally result is pi. Okay, so from here I think everyone have to calculate this integration. Therefore, I don't give more detail. All right. So for question C. Question C, now we can draw the reason D. So we should look like this. Because this is bounded by question C here. The solid between sphere, this sphere, and the hyperbonoid. Okay, so therefore it should look like this. So reason D is here. So we have a volume interval triple interval d 1 dv, and this equal to integration from -3 to 3 from minus square root 9 minus x power 2 and square root 9 minus x power 2. Okay, because look at here. Also, sorry, 9. Oh, yes. Need to go from square root 1 plus x power 2 plus y power 2. This is 19 minus x power 2 plus y power 2. Okay, 1 dz dy and dx. All right, so now we have from -3 to 3 is 9 minus x power 2 9 minus x power 2 here it is square root 3 minus x power 2 minus y power 2 minus square root 1 minus x power 2, sorry, plus y power 2. Okay, d by dx. Right, now in this integration, and this integration, and then you can see we use polar coordinates. Polar coordinates x equal to use polar coordinates. Use x is r cosine theta, and y equal to r sine theta, and then you get the v. Now is the integration from 0 to 2 pi. Okay, and integration from 0 to 3 square root 19 minus r power 2 minus square root 1 plus r power 2, and this is equal to -1/3 overall from 0 to 2 pi 20 square root 10 minus 19 square root 19 minus 1 d theta. Now you calculate this integration and then you get this 2 pi 3 times 1 20 30 equals 10. Yeah, that's the reason. It's okay. Any question?
Thầy ơi, thầy cho con thầy cho con xem lại từ đầu vậy này. Thầy tính ra cái x mà đi từ -3 đến 3 làm thế nào vậy?
So look at so we are or from here we find the intersection between this solid and hyperbolit. Okay, so I write here. Z is x power 2 plus y power 2 plus z power 2 is system 19. Okay, right here. And this one is z power 2 minus x power 2 minus y power 2 equal to 1. So maybe some mistake. Okay, now look at here. You have the first square x power 2 plus y power 2 plus g power 2 equal to 19 and z power 2 person minus x power 2 minus y power 2. Okay, so this equal to 1. Okay, so maybe some mistake here. Okay, so now we have x power 2 plus y power 2 times equal to 20. So therefore x power 2 plus y power 2 equal to 10. Oh, maybe it's let me check this correct. No, yeah, not 10.
I think 2x squared plus 2y squared equals to 18.
Sorry. Okay, sorry. Sorry, yes, exactly. Then we also sorry. This is 9. All right. therefore you can see when you project this here, and then you get this. You get this circle. Okay, this circle. Therefore, that's why x from -3 to -3 to 3 here. Okay, right? And y from -√9 minus x power 2 y to -9 minus x power 2 to √9 minus x power 2. Understand? It's explained from here.
Yeah, I understand it now.
For z, this is very easy because you access from here. Okay, you meet this parabola first, and then the sonist, the other sphere, this sphere, yes, this is sphere. Understand? Every x and y on this circle, and then you go from this direction, and then you meet this first and second. Therefore, that's why z from this to this. Everything is okay?
Yes.
Nó như này.
Dạ,
Nó
thưa
như
ơi.
này. Yeah. Sorry.
Em hiểu cho đó rồi.
Yeah. What's your question?
Cái phần mà đổi xem polar coordinate này em không có hiểu lắm. Cái đổi cận đó thầy.
Okay. Now, look at here. Theta here, okay? Theta here and r here, because we consider the whole circle. Therefore, theta is from 0 to 2 pi, right? Understand?
Dạ, cái này em hiểu.
Yeah, we consider the whole circle. Therefore, when theta from 0 to 2 pi and r from 0 to 3, here is 3, it's -3. So you can see we have the whole circle. Understand?
Dạ rồi, em hiểu rồi.
Yeah. So if you sometimes if you have consider only the half circle, then theta should be from 0 to pi, or sometimes it's the only this part, and then theta from 0 to pi over 2. So in this case, because we consider the whole circle. Yeah. So for the cheaper integration is similarly to double integration. Tức là mình sẽ đi từ dưới đi lên, mà bây giờ mình sẽ chọn một cái miền ở dưới này, sao cho mình đi từ dưới đi lên ở tất cả các điểm xy, Bây giờ nó giống như trước đây là mình quét nhà, đúng không? mình đi từ dưới này đi lên. Nếu mà mình chọn cái miền D mà tất cả các cái điểm ở trong này mà lúc nào mình cũng gặp cái đường này trước rồi thoát ra bởi cái mặt này, mà nó quét ở bên trong này hết, quét bên trong này hết, bên trong cái volume này hết, được không? Phải không? Thì lúc đó mình sẽ có cái tích phân từ đây này. Tức là cái này đầu tiên là có một cái miền gọi là miền R, rồi sau đó dy dx, đúng không? Rồi sau đó cái tích phân này trong cái miền R này nó access toàn bộ, lấy bất kỳ cái x y trong cái miền R này thì nó access cái surface này trước. Ví dụ surface này trước đây nó exist, nó thoát ra bởi cái mặt này, cái surface này. Và bây giờ cái R này là cái gì? Cái R này thì đây chính là cái này. Sau đó cái R này thì lúc bây giờ quen thuộc rồi, đúng không? Đây, cái R đó lúc bây giờ mình lại trở thành cái double integration. Mình thành cái double integration. Cái double integration bởi vì nó là hình tròn nên là ta sẽ đổi sang cái polar coordinates. The idea is very simple. Trước đây thay vì mình quét nhà thì bây giờ mình nói là chọn một cái miền D để mình đi theo cái hướng này lên thì toàn bộ cái volume này mình vào được hết, bất kỳ cái điểm nào ở đây mình đi thẳng lên thì mình đều chui được vào cái volume này, chứ nó không có đi ra ngoài cái volume này. Nó chui được vào nhưng mà lúc nào nó cũng gặp cái mặt này trước thì nó thoát ra bằng cái mặt này. Thì quét nhà cũng thế, đúng không? Quét nhà cũng thế. Đây ví dụ như cái đường này như thế, mình đi từ 0 đến A thì chẳng hạn như thế, trong toàn bộ cái miền này mình cứ quét với tất cả những cái đường này thì nó sẽ phủ kín cái này, phủ kín cái miền này, nó phủ kín cái miền này, nó phủ kín cái miền này, nhưng nó lại có, nó phủ kín cái miền này và nó có đặc điểm là nó đi theo hướng này thì nó đều gặp cái này trước và nó cuối cùng thì nó thoát ra. Thì bây giờ mở rộng nó ra trong trường hợp 3 chiều. Mình đi từ dưới này đi lên, chọn cái miền R này, đi từ dưới này đi lên thì luôn luôn nó gặp cái mặt này trước, nó thoát ra được cái mặt này, và lúc nào nó kín hết bất kỳ cái điểm nào trong đây thì nó sẽ quét kín cái volume này. Không? Mà muốn tìm cái miền này thì bây giờ lấy dao của cả hai cái surface này rồi mình chiếu nó xuống thì trục OX. It's okay. Cứ nhớ cái quy tắc đó thì bài nào ta cũng làm được. Vẽ phác họa là alright. That is question 2C. Okay. So question 3A. So 3A, what is it? 3. Number 3 is the following integral in the cylindrical coordinate. Okay, cylindrical coordinate. So the cylindrical coordinate is it? Do you remember? Nhớ học cái đó nha. Sphere coordinate. Cylindrical coordinate here. So in this case, we have a triple integration like this. Okay, this formula. And now for question 3a, then we have we should draw the graphs look like this. X here, Y here. Okay, so we have a circles like this. 3 minus 3, a half circle on OXY. Now see here. So this is look like this. We have a cone look like this. So this, you remember, this is the circle on our X, a half circle. So therefore, we have a integration. This is from 0 to 3. Integral from minus square root 9 minus x, y power 2, and now not x here, 0, y power 2, and square root 9 minus okay, so y power 2, integration from, now you can look at here, you assess this is from 0 to 9 minus 3 square root x power 2 plus y power 2. Okay, dz dx, not dy, dx and dy. Okay, so now by using the cylindrical coordinate, and then you get this equal to 0 to pi. Okay, and r from 0 to 3, square roots from 0, because here x is our cosine theta, and y is r sine theta, and z equal to z, cylindrical coordinate. Therefore, z from 0 to now, because x is r cosine theta, y equal r sine theta, therefore this is 9 minus 3r pi. R Jacobians now is r. Okay, I write here, maybe it's better. dz times r dr d theta, because the dx times dy now becomes to r dr d theta, right? That is cylindrical coordinates. So therefore, this is a integral from 0 to 3, integral from pi 0 to 3, 9r minus 3r power 2 dr d theta. So finally this equal to 27 pi over 2. It's okay? Question 3b. Now 3b, you can draw the volume here. So it's look like this. So one here. Okay. This is a minus 1 here. This 1. Okay. Yeah. So therefore we have a integration. This is a minus 1 to 1 for x, for y, integration from minus square root 1 minus y power 2 and square root 1 minus y power 2. Okay. And integration from minus 1 to 1. Go to z from minus 1 to 1. Now this is x power 2 plus y power 2 dz dx dy. Okay. So this is equal to, now we change to the cylindrical coordinates, and you get 0 to 2 pi, because you can see this one is this exactly is equal to the circle with the radius 1, and 0 to 1 integration from minus 1 to 1 dz. Okay. X power 2 plus y power 2, so now is r power 2 times r dr d theta. Okay, so calculate this integration. It's very easy, I think. So to get the final is to 4 pi over 5. Understand? Question 4a. 4a is evaluate the following integrals in spherical coordinates. Now spherical coordinates. Right here. Yeah. In this case, we have a z equal to rho cos phi, r equal to rho psi theta. Okay, So exactly x, now you can write more detail. X equal to rho psi phi cosine theta, and y equal to rho psi theta phi psi theta, and z equal to rho cosine theta, and then you get this fair. Okay, this fair. So now using this spherical coordinates, then we have integration on d of x power 2 plus y power 2 plus z power 2 pi over 2. Alright, v. So this exactly now, because when we change like this, then you get the values integration from 0 to 1. Remember, this is a integration from 0 to 2 pi, integral from 0 to pi. Okay, this is a rho power 2 power 5 over 2, therefore rho 5. Okay, here rho power 2 times rho power 2 psi b d b theta 0. Okay, rho now takes value from 0 to 1, theta from 0 to 2 pi, and phi from 0 to 2 pi here. Okay, so now from here, then we have this is triple integration. Then you just calculate this integration, and then you obtain this exactly is equal to pi over 2. It's okay. So remember when hello. Có cái gì không? Anh có. Đang bận. Okay, so we observe and we see that when our integration contain these terms, then we should think about to use this spherical coordinates. Understand? Similarly, for the question 4b, and then you can see that this is the contain the terms x power 2 plus y power 2 plus z power 2 power minus 3 over 2 dv. And similarly, you use this change of variables, x like this, and y like this, and z like this. And then finally, this become to triple integration, and then you get a final result is 4 pi Okay. 2. Okay. So the argument is quite similarly to the question 4a. Right? Any question? Number 5. Number 5. So we change the reasons by changing variables. So question, the first question. Yeah, we calculate this integration. Here R is square with the verticals, these verticals, and now we use the change variable x equal to u plus v and y equal to u minus v. So look at here, we have the reason R is look like this. So okay, the reason R is look like this. Right. So here reason R here. R is look like this. Now by using the change variables, and it's become here x, remember x, and here y. And now when we change x equal to u plus v and y equal to u minus v, and in this coordinate OUV, the R now becomes to this S. 1 here, 1 here. Understand? When we change the variables, then the reason R now become to this reason S. So you can see S is very beautiful reason. This reason is easy to calculate the integration. Tức là chúng ta đã biến một cái miền phức tạp, cái miền không có đẹp thành một cái miền rất là đẹp này, trong một cái hệ tọa độ khác. Bằng cách là đổi biến, tức là quay cái trục hoặc là một cái cách nào đó đổi biến đi để cho cái hệ tọa độ này thành cái hệ tọa độ này. Right. So now we have the Jacobians u and v. So this is equal to determinants. This is 1, 1, 1 minus 2. Do you know how to get this determinants? Remember? If you forget, so this is here, Jacobian. Here, Jacobian here. du, dx in du, dx dv, dy in du, dy in dv. So look at here. So when we have x equal to u plus v, y equal to u minus v, dx in du is 1, dx in du is 1, and dy in du is 1, and dy in dv is sorry, this should be my here. Y equal to u minus maybe it's 2v. 2v is not 2v. No, let's see. I have a 2. No, u minus v. Why is this No, yes, this is, sorry. This should be 1, minus 1. This is minus 1. So, yes, exactly, minus 1. But not minus 2. Now you take this 1 times minus 1 minus 1 times 1. And this is minus 2. Yeah, exactly. So therefore, our integration I becomes to integration from 0 to 1. 0 to 1. X, y, x u plus v times u minus v. Square root of Jacobians minus 2 d v du. Okay, so from here it is very easy to calculate this integration, then you get 0. Okay, so question E. Question B, our reason R is look like this. R is look like this. 2. Now here is x, y. Now it's become 2. This one. S is a square. 1 and 1. U and V. By changing the variables is like this. Now from the changing variable, then we have a J Jacobian JUV equal to the x in the u is 2, the x in the v is 0, the y in the u is 2, the y in the v 4. Therefore, this is equal to 8. Okay. Then we have integration in R of x power 2, y power 2 di becomes to integration of 4 times integration 0 to 1 of u power 2 times 2 v plus u dv du. Okay, so calculate this integration, you get the result 112 over 3.
Cô thầy đề là x bình y chia a thầy ơi.
Không có cái này đúng không? X power 2y. Okay. Question C. Question C is look at our reason R in x and y. Our reason R is look like this. R look like this by changing variables. So the reason is very beautiful. Is look like this. S in here, U and V. Therefore, we have a Jacobian chase. Now is 1 minus 1 and 1 and 1. This is exactly equal to 2. Therefore, our integration on R of square root x power 2 minus y power 2 dA and to the integration from 0 to 1, the integration from 0 to 1 of square root, okay? So it's long. U plus V power 2 minus U minus V power 2, okay? dV du, and finally you get result 60 by left. Okay, so this changing variables, the idea of changing variables. So we use the suitable transformation x and y, and then you can convert this reason is not beautiful to the beautiful reason in the coordinate u o v. Okay, so in this coordinate, so it's very easy to calculate. But for the transformation, we have some coefficient. We call this is Jacobian. J is like this. Đúng là J is Jacobian J, nó là một cái gì? Let's see. Một cái hệ số mà nó hiệu chỉnh, một cái hệ số nó hiệu chỉnh, giống như là cái phép co, phép giãn, phép quay, phép biến hình. Đó. Nó có một cái hệ số nó biến thành cái hình này thành cái hình đẹp này. Thì trong cái tọa độ này chúng ta rất dễ dàng lấy tính được cái tích phân. That is the main idea of changing variables. So for example, Jacobian is very important. So you can see in the Castorian coordinate to polar coordinates, the polar coordinates. So this is the special case of changing variables. Okay. Trong cái trường hợp này thì nó là cái phép biến hình tuyến tính. Biến hình tuyến tính tức là cái coordinate này nó vẫn thành cái Cartesian coordinate. Chẳng qua chúng ta dùng cái phép co quay các thứ nữa không. Nhưng mà nó vẫn là còn cái polar coordinate hoặc là cái cylindrical coordinates is a special case. Special case of changing variables. So that is not linear transformation. In this case, this is a linear transformation. So therefore, the term r and d theta are here exactly the Jacobians. Okay. Trước chúng ta chưa hiểu tại sao lại có thêm cái hệ số a trong cái tích này. Rồi là dx dy bây giờ nó bằng không? Trong cái trường hợp tuyến tính này thì dx times dy nó bằng cái Jacobi này 8 lần cái này. That is the main idea of changing variables. Okay, any question?
Thầy ơi, để cho em xem lại câu 5A đi thầy. Em tính ra kết quả nó khác thầy.
Yeah.
Yeah.
Remember here is an absolute value. This is a determinant notation. This is an absolute. Therefore, minus the 2 becomes 2. Everything is okay.
Em không có lấy giá trị tuyệt đối. Cảm ơn thầy.
No. So any question?
Ủa thầy, lúc thi mình có được dùng graphing calculator không thầy?
Cái gì?
Dạ, lúc thi mình có được dùng cái gì để vẽ đồ thị không thầy? Để làm những câu như là vẽ spherical coordinate hay là cylindrical coordinate ấy thầy?
Em vẽ ra giấy thôi, vẽ ra giấy, không cần phải viết vào trong bài thi. Viết cũng được, không cần viết cũng được, chủ yếu mình vẽ ra để mình hình dung để tính toán cho dễ, hiểu không? Phác họa ra để mình hình dung, để mình tính thử nó dễ. Ok. Rồi ta nghỉ giải lao một chút rồi ta sang cái chương cuối cùng. Chương này là một chương mà nó cũng khá là phức tạp và là khó, nên là hết sức để chú ý.
Dạ thầy ơi, thầy cho con sang câu 3B được không thầy?
Cái gì đó. Thì cái vẽ được phác họa nó ra được cái hình này thì mình hình dung nó sẽ dễ, thấy không? Alright. Rồi ta nghỉ giải lao đến 9:50 nhá. Từ 9:37 đến 9:50. Ok. All right, so we continue. Okay, you ready? So this chapter is I think it's more difficult than last chapter. Therefore, you should be very careful. Okay. All right. So chapter 16 or chapter 5, the vector calculus. So the first session we study vector fields. This is a very new concept for you. So imagine that when you when you go out and then you see the wind blows, or the wind, or you are on the plane, and then you see the wings, the air blows around the wings. And now look at here, it look like this. The vector field is look like this. Understand? So this is a velocity vector field showing in San Francisco Bay, and the patterns is look like this here. So it means that if you are here, or here, and you if you go around, if you go along the vector fields, and then you may go faster than you go along the opposite sides of vector fields. All right. So now the associated with the vector field associated with every point in the air. Therefore, we can imagine a wind velocity vector. So this is an example of velocity vector field. Now, more exactly, we have a definition. We have a definition of vector fields. So now let's D be assessed in R2, a plane region, a vector fields on R2, either a function f assigned to its points x and y in D, a two-dimensional vector fx and y. In calculus 1, and if we have a point x, and then you get point here fy, or you have a point x and y in the plane, and then you get the value f at x and y. So it means that so it means that in general we have a point in n dimension Rn. So f on Rn, then we get this value f here. Value f here. This is in R. The value is in R. not in R2, not in R3. However, in the vector fields, so it means that we have a point x and y in R2, and then you get a vector f x and y in R2 or maybe in R3. Okay, so we call this is a vector field. So it means that a function now is it's a vector function, right? So this is a definition of vector fields. So the best way to picture vector fields is to draw the arrows representing the vector x, y, starting at the point x and y. Okay, so here, look at here. If we have a point x and y, then we have a values. So we have a values f, x, and y. This is a vector. This is a vector. So this vector, we have the length of this vector. So here's the length of this vector and the direction, the direction, and then you get this. This is of course the vector field. So every point you do like this, and then the set of the arrows. So we call this is a vector fields on R2. So in general, we have a vector functions f, x, and y. So we can write this in terms of a component function p and q as follow. And here f, x, and y is the p, x, y, I, and q, x, y, j. Or we can write like this. This is a vector. Okay. So for source, we can write this f equal to p, I, and q, j. So remember that p and q is a scalar function. It's a scalar function of two variables. And sometimes we call this scalar fields to distinguish with the vector fields. Okay. So now we have a definition in extension of an extension of this definition. We have E is a subset in R3, and the vector fields on R3 is the function that's assigned to each point in E, okay, and a three-dimensional vector f, x, and y, and z. And now similarly to this, we also have this representation. We have three components of p, x, and y, and z, and q, x, and y, and z, and r, x, and y, and z. Okay, so the vector fields are on R3 is this look like this. Okay. So with the vector functions, we can define the continuity of vector fields, and so that f is continuous if and only if it's a component function p and q and r are continuous. So if p and q and r is continuous, then we say that f is continuous. So we sometimes identify the points x and y and g with the position x. So the bow x denotes the vector with the point with the coordinates x and y and g, and we denote the bow fx instead of vector field fx and y and g. Okay, so now then the bow f becomes a function that assigns a vector fx to a vector x. So x now becomes to x fx. So the notation is quite similar. It's a function of one variable in calculus 1. Now we consider an example. An example. A vector field on for simple, we just consider a vector field on R2. Here we have a f, x, and y. This is minus y I plus xj. So now we need to describe exactly the vector fields f, x, y is like this. So the picture is look like this, and how to now you can see how to find this vector fields. We look at here. Let's see. Right here. Yeah. Now we choose x and y are the point x and y. For simple, we tested the point x and y is 1, 0. And remember that's f equal to minus y I plus xj, okay? Or exactly, you can do like this. X is minus y and x, okay? So therefore, when you take the point, 1, 0, and then you get f, x, and y is 0, 0, 1. 0, 1 now, look at here. Here. F, the point 1, 0, 1 here. The point 0, 1 here. Sorry, 1, 0 here. 1, 0 here. This point. And now f, you can see f is exactly, you can see this exactly is equal to 1j, equal to 1j. Therefore, this vector parallel to OY with the length 1. Therefore, you can draw this vector f1, 0 like this. Understand? Here, look at here. J, f at this point, f become to 1j. Now the vector j here, because f is 1j, therefore it's the parallel to the axis OY. Therefore, we can really represent the vector f1, 0 is look like this, and the length is 1, right? So similarly, what happens if x and y is 2, 2? So this one is become to 2i plus 2j, okay, 2i plus 2j, and the length of f is square root of 4 plus 4 equal to 2 square root 2. That is the length. Now, how about the direction of f? The direction of f here is 2, 2 here, f2, 2. The length of f is square root 2. 2 times square root 2, and the direction, and here the direction, this is a minus 2j plus ij, therefore the direction is look like this, okay, with the length. So therefore, now at this point we can draw the direction of f at point 2, 2 with the length is square root 2 times square root 2. Okay. So for now, look at here. If you are, for example, if you are here, and then it's different from you are here. Maybe you are here. the direction and the fox. Okay, so that therefore you can see the length of the length of f. Yeah, the length of f and the direction. So you can see this point is different from this point. This point has a length of f is 1, and the length of f is square root 2. Therefore, imagine that if you have the air funnels funnel this direction is look like this, then if you are here and the force is the difference. If you are here and then by the air, then you can do explode you go to this direction with the force. This is the 1 here. If you are here, if you are here, you cannot you cannot go by this way. You have to go by this one because it's the direction and the force at this point and this point is different, right? So similarly, you can choose this point as it become to this, then here. So every point, you take every point on the plane of x, y by this law, you can represent the vector fields, Okay. For if you want, you can use Maple to plot the vector fields. Okay, open the Maple. Because if you draw by hands like this, you choose this value and then draw is maybe take more time. However, by using your computer, then you can plot every vector fields. Okay, so if you don't know how to use the command, and then you can ask field plot. Okay, field plots, and then this gives you field plots. The syntax. Okay, syntax here. Right, I copy this one. Before that we download the package. Then now, what is f? F is if you don't know more exactly the syntax, and then you can see the example. Okay, so now the vector field push on the list. Okay, in here I push on the list. This is minus y and x. Okay, and I take x from maybe it's minus 3 to 3, and y from 3 to 3. Okay, and what is the option? The option here is option is control the behavior of vector fields. So now look at this picture, and we don't need to push an option. Therefore, this is maybe. Then, oops. Why is there? plus. Sorry, here it should be minus. Which look like this. So look like this, you can see the vector fields in this case. If you want to change, and then you maybe, what happens if I change the minus x here? So it's a difference. It's a difference or different direction. It's a difference that it changes the direction. So the last vector field is the direction is like this. When you change like this, it's change direction. Understand? So therefore now you can use Maple to plot the vector fields, and from here and you can see the direction of the vector fields. So in this case, the direction of the vector field is okay. So all right. So now to confirm this, is we take the dot products of the position, and here x is a xi plus a yj, and f is like this, and we take the dot products, and then you can see that's you can see that x times f x is or equal to 0. Therefore the vector fields, the vector field f x and y is now orthogonal, or is it now perpendicular to the position of vector x y, and this is therefore the tangent. Therefore we see that it's a tangent to the circle with the center, or is in radius x, like this. Okay, so we have the length of vector fields exactly is the length of x. Okay, so therefore the magnitude of vector f x and y equal to the radius of the circle in this example. Okay, so now in this example, imagine the fluid flowing steadily along a pi, and now denote the v, x, and y and g velocity vector at the point x and y and g. Okay, and then v assign a vector to each point x, y, g in a certain domain E. Okay, the domain E is the interior of the pi, and now v is a vector field on R3, so we call the velocity field. So this look like this, right? So for the speed at any given point is indicated by the length of your arrow, right? So next we consider example for the Newton law of gravitation states that the magnitude of a gravitation force between two objects with the mass m and capital M is the force F is given by this formula, and here R is the distance between the objects, and G is the gravitational constant. Okay, so now let's x position x and y and g, then we have R equal to the length of x. Okay, so therefore we have a gravitational force exerted on this second object vector towards the origin, and we have unit vectors in this direction. This is like this. So therefore F can be represented by this formula. Okay, so this is this is an application in physics of vector fields. So now now we have a x. This is a vector x can be represented by this. So the length of x, and this is therefore the vector field F's is can be represented like this, right? So here you can see this is a description of vector fields. So let's look at this, right? So this is for three dimensional you can use your plus. So you just put the 3D here, and then you get this, the graphs of vector fields in 3 dimensions. And let me see. Maybe this is I think, for example, if I x and minus z, and maybe z is plus 3, for example, and g from maybe 0 to 3, and see. Yeah, this is right. You can draw the vector fields of in 3 dimensions. Okay, so here is it. For example, if I choose the vector field is look like this. Okay, so Maple can help you to plot the vector fields in 3-dimensional or 2 dimensions. All right, so now gradient fields. What is a gradient field? If f is a scalar function of the 2 variables, so we remember that's a gradient of f. So we have this notation, grad f. It is defined like this. This is a vector of partial derivatives. So gradient f is can be represented like this. Okay, so partial derivatives in x and partial derivatives in y. So therefore, the gradient f is really a vector field. So this is special case. The gradient vector is special case of vector fields on R2. So we call this is a gradient vector fields. So similarly, in 3 dimensions, so we also have gradients in vector gradient vector fields in 3 dimensions. So we have a partial derivative in x and y and g. Okay. So now, for example, find the gradient vector field of f x and y is like this. So plot the gradient vector fields together with the contour map of f, and see how are they related. So now we have a gradient vector fields f. This is a partial derivative of f in x and y, and here from here you obtain these results, right? So now we have these curves. This is a contour or a map of f, and the blue arrows is a gradient vector field. And look at here, and then you can see this is bigger. And you can see when we have a tangent, we have a tangent here, this is point, the tangent of this curve, and the gradient vector is an orthogonal, it's a tangent every point. Yeah. So remember in the last chapter, the vector fields, the gradient vector is always orthogonal to the tangent, the curve. So such is an example of special vector field, right? Okay. Now, remember a vector field we call is conservative vector. So should remember this in these concepts. A vector field is called a conservative vector field if it is exactly the gradient of some scalar function. So it means that it means that if you have a vector field f, and now vector field f's, if vector field f's exactly is a gradient of some function f, then we call f is a conservative vector field. So it means that f and y can be represented by fx I plus fy j. Then we say that f is conservative vector field if there exists a function f such that the vector field can be represented by this. So this is exactly the gradient vector f. Okay. This is true for all x and y. It's true for all x and y. So now in this case, the function f is called potential function of f. So we should remember that not all vector fields are conservatives, but some vector fields is conservative vector fields. Remember, not all. So in case we can given the vector fields, and we can find a function f such that the gradient of f small f exactly equal to the vector field. Therefore, we call the vector field is a conservative vector, and the function f is a potential function for f. Okay, so now for example, we are if we look back, yeah, yeah. We have a vector field f is this. Then now we choose a function f, small f is like this. Then gravitational fields of field f can be represented like this exactly. Then we say that in this case we have a gravitational field f. This is a conservative vector field, and the function f small f is the potential function to gravitational field f. Okay, so now understand? Next session we consider we study 9 integrals. So this is a very interesting topic. So now in this session we will define an integral as that is similar to a single integral, except that instead of integrating over integral a and b. Therefore, now we can see that this integration on a b is a special case of the 9 integrals. So assume that we have a curve C, given by parametric equation x equal to xt and y equal to yt for all these in A and B. So now we have a vector equation RT is xt I plus y dj. Okay, now we assume that C is a smooth curve. Okay, and C is smooth curve. It means that the derivatives of vector equation this is continuous. So it means that xt is a continuous, yt is a continuous, and of course r right is not 0. So for this condition we say that C is a smooth curve. Smooth curve is smooth like this. So it's every point we have there exists the derivatives x and y. Okay. Now here for all these in A and B. Now we will divide the parameters interval A and B into n sub intervals di minus 1 di. So we have xi is equal to x di and yi to y ti, and then we see that we have a corresponding points pi at xi and yi. So now divide C into n subs curves with the length delta s1, delta x2, and so on. So like this. Okay. Then we are similarly to previous definition of integration. Then we define Riemann sums f at xi star, yi star, and xi star and yi star is at any point in each length, next length delta si. Then we take this sum and we call this is a Riemann sum. And now when the interval ti is minus I and ti is small enough. So n is n subs intervals go to infinity. Then if the limit exists, then we call this is a integral f along C. Okay, along C. So therefore now we have a full definition of the integration f along the curve C. Now let f define on a smooth curve C given by equation 1. Okay, given by equation 1 here, and then the integral of f along C define like this. So we have a length. We have a length of the C. Length of the C L is the integration from A to B square root of derivatives of xt power 2, derivatives of yt power 2 dt. So this is the length of the curve C can be calculated by this formula, right? So now similarly we have this integral of function f on the curve C can be calculated by this integration from a to b in t, or f xt and yt, the square roots of derivatives x in t power 2, derivatives of y in t power 2, right? So this exactly equal to integration from a to b f. We can write like this: fxt it yt is the length of derivatives rt dt. So this one exactly equal to length of the vector derivatives vector rt. So you can if this formula is very difficult to remember, and then you can remember this formula. Okay, this formula. In case f is equal to 1, f equal to 1 for all x and y, then we obtain this integration exactly the length of L. Okay. So quite similar when C is only in interval A and B. Okay, A and B. So C here is a line. Then the integral of f from A to B dt. And now when f equal to 1, exactly equal to b minus a. Therefore the length of C now is equal to b minus a. It's special case of this integration. Understand? So therefore, you can see the definition of integration for one variable in calculus 1 is a special case of this integration. Okay. In case C becomes to 9 A and B on the axis and x. Right? So therefore, to calculate this integration, we follow 3 steps. The first steps we should
tính độ dài.
Sorry.
Có hay nhỉ?
What happened? Okay, so we have a first steps. The first step we should parameterize the curve C by putting x equal to xt and y equal to yt, or vector equation. This is look like this. Okay, and the second steps, you calculate the derivatives of vector rt, and then calculate the length of the derivatives r. Okay, vector r, And the last step, you apply this formula, then you can find the integration of f on the curve C, Okay. All right. So that's it. And now we go to our example here. So this explanation f. Okay, so this example, and here, and I think you can read this explanation later by yourself. Okay, so this picture is very interesting to interpret the integration of the function f along the curve C. When the curve C is exactly aligned, then it become to function f here. It become to the normal integration. So from A to B, you can see from A to B is we divide like this. So the curve C here, you also divide the curve C like this. And every point x and y on C, then we get the function f, x and y. And we have the distance between the upper point x and y on the curve C and the surface f, the surface f x and y. Okay, so this is the curve on the surface. Understand? So remember, it's just a different from here we have a set D, here, and then we have the surface on D here. So therefore we have a double integration D of f x and y dx dA. Okay, so now we don't take all value x and y in D. We just take the value of x and y along the curve C. This, and then we obtain this. We obtain the curves f x y with respect to the curve C here, and then we calculate the area of f x or y to between on f x and y and the curve C. Understand? Tức là trước đây thì mình lấy cả cái tích phân cả cái x y trên cái biên D này, thì mình sẽ có một cái surface này, thì mình sẽ có cái double integration. Nhưng bây giờ mình không có làm như vậy, mình chỉ cho x y chạy trên cái curve C này thôi, thì sẽ có một cái curve ở trên cái surface này. Cái curve này chính là cái f x and y. Đó. Và bây giờ mình sẽ vẽ nó, thì nó sẽ có một cái mặt cắt. Bây giờ mình sẽ tính cái tổng diện tích của cái mặt cắt. Đó, mặt cắt. Đó, thì đấy là gọi là cái tích phân dọc theo cái đường C, đường cong C. Trong trường hợp f bằng 1 tức là nó co lại xuống đây. Thì nó chính là C, f bằng 1. Nhìn đây cái độ dài nếu mà nó bằng thì nó chính là cái C. Thì nó bây giờ nó sẽ là cái lang của cái curve C này. specific. Okay, now we go to the example 1. In example 1, now we need to calculate this integration of this function on the curve C, and in here C is the upper half of unit circle. Okay, unit circle. So here, like this. All right. So look at here, we have 3 steps. The first step we should have obtained. We should have a parametric of the curve C. So to have a parametric of the curve C, and here because it's x power 2 plus y power 2 equal to 1. Therefore, if we choose x equal to cosine t and y equal to sine t, not r cosine t, not r cosine t, r sine t. Because if you take the r here, then it's not the curve, and this is on this reason. Therefore, when r equal to 1, then this is this curve. When r equal to 1/2, this is this curve. So now it's just this curves corresponding to r equal to 1. Therefore, that's why we don't have a general value r here. All right. So now we have a parametric equation of the curve C here, and then next we calculate the r prime t. R prime t is the minus sine t and cosine t, and then we calculate the distance of the length of this vector. Okay, so therefore now you can see t from 0 to pi 0, because this curve, this is a half of the circle. Therefore, t from 0 to pi are 2 plus the x power 2 and y becomes 2 cosine power 2 and sine t. Here is the length of derivatives rt. Then we get this result. Okay. This I'm going to results. Okay. The result is like this: 2 pi plus 2 over 3. Right. Next, we suppose that is the curve C is a piecewise smooth curve. You can see on the whole curve there is some point. This point is not smooth. The curve C is not smooth at this point. Maybe this point. Therefore, we see that the C is a piecewise smooth curve. Now let's say the C1, C2, and Cn. Therefore, to calculate the integral function f on the curve C, then we need to separate into the sum of integral f on this smooth curve C1, C2, and Cn. Okay. So that is the idea when C is not smooth. So this is just smooth on piecewise curves. Okay. So this is I ignore this is the mass. You can read at home. Okay. So the definition of mass. Okay, mass center. I left this this topic that you can study at home. It's not difficult. It's just a definition of definition of mass amps, right? So now, we if we have a function f along to C, integration of function f along C with respect to x and y, then we have an integration of C of fx and y dx is a limit of f at x I star and y I star times the delta x y, and similarly to the integration of f with respect to y. And the first integration here, this integration here, you can see the ds along C, and now we just consider with respect to x, with respect to x. Where is this? Then we yeah, then we have a definition, new definition in case f is for integration of f along C, however, with respect to x and y. So now when we want to distinguish the original integral f x and y, c and ds from these equations, so we call this is a line integral with respect to arc length. Okay, length. So now we have a parametric equation of the curve C. We have x equal to xt and y equal to yt. Then therefore dx equal to x prime t, dt, and dy is y prime t dt. Therefore this integration now becomes to this. Okay, become to this. So therefore we have here x fx and xt yt and x prime t yt dt, and this is with respect to y now become to this, and therefore we have an integration, the cp x and y in general. We have this integration of function p x and y dx plus integration of q x and y dy. This equal to integration of c p x and y dx plus the q x and y dy. So it is look like this. So we have the curve C here. The curve C here is look like this. Curve C here, and now we go from this point A and B. Okay, so A and B. Now you go along the curve C, and then A go to B along the curve C. Now, if you go to A and B by this direction, and then you have a two way to go from A and B by this direction and this direction. Okay, therefore by these directions, and then you get the integration with respect to x and y. Okay, so now in particular we often need to parameterize a line segment. So it is useful to remember that a vector representation of a line segment that start at R0 and n as R1 given like this. So you can see for all t in 0 and 1, when we have a R at the 0 equal to R0 and R at 1 equal to R1. So therefore we have this point A and B. So we use the parametric equation RT. Then we choose it to do like this, and we obtain the direction is from A to B here. For example, here's the R0 and here's this R1, for example. Okay. So this is in general. This is parametric equation. So the curve C, this is from the point R0 to R1. Okay, so it's look like this. So therefore, now in general, given the parameterization x equal to xt and y equal to yt, and here for t equal to from A to B, then when t equal to A, and we get the point A. When t equal to B, we get the point capital B. Then you can see that's because the t from A to B, then we move on the curve from the point A to B. Understand? So if we change the value for t, then we get the curve is now from the direction from B to A. Then we denote the minus C. The minus C is mean that we go from the point B to A. And similarly to now, you can see the integration from I write here then I choose this is let to see x0 and x1. Okay, so the function f x dx. Okay, so now when you change, so this is the minus from x1 to x0 fx dx. So because when we take the integration of f x0 here, x1. Okay, so the value x from x0 to x1. If you take the value from x1 to x0, then the size is changed. So similar the idea. Then we denote the curve. We have oriented curves from A to B. If we change the direction, then we know the minus. Right? Understand? So therefore, look at here. Then we have an integration on minus C f x and y equal to minus integration C. The idea is hiểu không? Cho nên là trong cái tích phân theo cái đường cong này thì cái hướng là quan trọng. Khi ta đổi hướng thì cái đầu nó phải đổi. It's okay. However, now we integrate with the respect to arc length. The value of the line integral does not change when we reserve the orientation of the curve. So it means that the integration of minus c f x y ds. Remember here ds, here dx, dy. So this is ds, not dx and dy. So this integration is with respect to x, with respect to y. So when we take the integration with respect to x and respect to y, then when you change the direction in C, then it's different. So look at here, this picture here. So from A to B, so if you change from here, then you can see from B to 0. So therefore, this is come back to the integration in calculus 1 with respect to dx and dy. So however, if ds here, it means that we don't take the integration with respect to x and respect to y. We take the integration on C, along C. So that is a special properties. This is the different from the calculus 1. Okay. So now integrals in space. So in space we have x equal to xt and y t and z equal to zt. Therefore, our vector rt is look like this. Okay. So therefore now we have 9 integrals of f along c. This is an extension of the integration f along to c on the 2 dimension. So therefore, we also have this formula. So these terms is the length of the derivatives rt. So in case now for source we can write it f of rt times the length of derivatives vector rt. So in case f is equal to 1, then we obtain the length of the curve C on 3 dimensions. Okay. So and now the integration along C with respect to x similarly to the last case, x and y and g, and then we obtain this formula. Okay. Now, for example, we need to calculate the integration of this function on C, and here C is a circular helix given by this equation, and x equal to cosine t and y equal to sine t and z equal to t. So look at here, and then you can see that we have a curve or on a cylindrical coordinate. Okay, so the curve C is look like this. Curve C look like this. So therefore we have a t from 0 to 2 pi. Now this integration become to this integration. So from here it's not difficult to calculate this integration. All right. So it gives us result. Yeah. Square root 2 times pi. Okay. So now next is very interesting and important. 9 integrals of vector fields. So we know that the works done by variables fox fx in moving a particle from A to B along the axis x is a w is a integral from A to B of fx dx. So this is the application of integration in physics. So now an extension of this integration. So we found that the works done by a constant Fox f in moving your object from a point P to another point Q in the space. So we have a F equal to W equal to F's vector F's is the dot products with a D, and here D is a vector D is a P vector P and Q. So now because it's F is a vector field and F is equal to P Q and R. Okay, this notation is different from this notation. The P is a function, Q is a function. Okay, and now we have a definition of a 9 integrals of vector fields on the curve C. On the curve C is this. Okay, so we divide the curve C into small curves, and it takes any point here, and then here we get the value of a vector field at this point, and then we make this is the Riemann sum, F times D, and here is T is the unit tangent. Okay, on the curve C, and then we have a work W. Now this is the integration of F times the vector D x y and T. So like this is the unit tangent vector. So D is D exactly is equal to R prime T divided square root the lambda of R prime T. Okay. So like this here, the tangent here. So the vector fields here. So when we move along this curve, and we have a tangent, and then the F here, therefore works. We have a works W. We have a works W exactly. It's just the sum of dot product. Dot products F times vector the T, because it's the object move along the curve C, then for work we take the integration on C. So for source we can write like this, right? So now because R equal to XT, I, Y, T, and ZT, therefore T is equal to R prime divided the lambda R prime. So therefore we can have W like this. So Y is like this. So look at this integration. Look at this integration. It's quite similarly to from A to B, a function f RT R prime T dt. Chúng ta thấy rằng là cái công thức này nó rất là giống với cái tính tích phân của cái hàm f trên cái curve C. Nhưng mà bây giờ cái f này nó trở thành vector field. Thì lúc này cái vector, because this is a vector, sorry, this is lambda. So this becomes this is the dot product. này thì nó là one dimension. Therefore, we take the length, and here we take the dot product. This is a vector. This is a vector. Right. So we have a definition. Let F is a continuous vector field defined on a smooth curve C given by the vector function. So we have a parametric equation of a curve C. Then the integral of vector field along C exactly is equal to integral of dot product F dr. And because R is C is a smooth curve, then for dr equal to r prime dt. R prime dt, then we can write like this. So for source we have F is time t. All right. So example. Now find the work done by the Fox field F is like this. In moving a particle along a quarter circle. I write here. Look at here. Okay, so so what happened? Look at here. How to draw this? Okay. Now, if we have here we have a vector fields here, and now if we have a curve C, is look like this. For example, now we don't move in the vector field. This particle move on the C. Therefore, every point here, you can see this is the direction. The force on this particle is different to the force at this point. Understand? Therefore, sometimes you can see here is because it's the same direction with the same direction to the absence. For it's move faster than this point. So therefore, we need to calculate the work on the whole curve C. That is the idea. Understand? To do that, we
thầy nói lại em chưa hiểu.
Đây nha. Cái ý nghĩa vật lý của nó. Đây nha. Thì bình thường chúng ta có cái vector field thì nó sẽ có cái hướng là đi như này, đúng không? Tức là mỗi một cái điểm như này, một cái điểm như này thì cái lực của nó sẽ tác động theo cái hướng này, đúng không? Mình cứ tưởng tượng như là đây một cái hướng gió đi. Mình đang đứng ở đây thì cái gió nó sẽ đẩy mình như này. Đấy, nhưng mà bây giờ mình không có đi theo cái này nữa, nhưng mà cái vấn đề là mình sẽ đi theo cái curve, này, chứ không phải mình cứ đi theo cái hướng gió này, tất cả cái hướng. Nhưng mình sẽ chọn một cái hướng là cái curve này. Thì mỗi một cái điểm ở đây thì rõ ràng mình thấy rằng là cái điểm này với cái điểm này nó khác nhau. Bởi vì sao? Bởi vì cái thầy vẽ nhé. Nó có cái tangent đây, đúng không? Đây là cái F, thì cái tangent này với cái F này, cái T này, đúng không? Nó là cái tại mỗi một cái điểm thì cái lực của nó sẽ như này. Nhưng mà tại cái điểm này, cái này nó sẽ đi nhanh hơn bởi vì hai cái vector này nó cũng thiếu. Nhưng mà tại cái điểm này thì cái nhìn thấy cái tangent của nó như này. Nhưng mà cái Fox thì nó như này. Cho nên là nhìn như cái chỗ này thì nó sẽ trượt tiêu, đúng không? Nó sẽ trượt tiêu. Nhưng mà bây giờ mình muốn tính là toàn bộ cái lực, toàn bộ cái công trên cái C này, khi mà cái object của mình nó move on trên cái C này, thì mình sẽ có cái tích phân nên là sao đó in án làm gì đâu, mình cứ tự vẽ này. Thì mình mới có cái tích phân này F EDT đó trên cái A and B. Khi mình đã tham số hóa rồi thì nó từ điểm A đến điểm B này, thì nó tương ứng với lại cái giá trị T, nó sẽ đi từ cái giá trị A đến cái giá trị B này. Đó. Nên thực ra là mình cái ý nghĩa vật lý của nó là như vậy. Okay, so in case if we have a vector field, like this, and now our particle moving along a quarter circle. Các em có thể vẽ cái bubble, các em vẽ cái vector field này nhá, rồi sau đó các em vẽ một cái quarter circle này. Bây giờ mình tính công nếu mà cái particle này nó move along cái quarter circle này. Okay, so when particle moving along the quarter circle, then we have a RT. This is a cosine ti times sine t chase. And here it takes t from 0 to pi over 2. Now we have a FRT from here. We have FRT like this, right? Ups. And derivatives of RT is like this. So now we have a dot products of the work of the particle along C is F times dr dot products, because this is two vector. So this is equal to dot product of this vector and then derivatives vector RT. And then now, because you know F RT, you know F prime T, and you take the dot products. Remember dot product. Còn nhớ cách tính dot products không? Cross product and dot products. Nhớ hai cái đó nha. Okay, then we get these results. Okay, these results. So now this is very easy to calculate. It's minus 2 over 3. All right. So now finally we note that the connection between the 9 integrals of vector fields and 9 integrals of scalar vector fields. So suppose that a vector field F's on R3 given by this. So therefore we have a integration C F dot products, the dr is like this. So because F is have a representation, and then we get this representation. Okay, so look at here. F have a representation in I and J and K because it's a vector, and R prime T's we also have a representation. It looks like this. Therefore, now this entity now becomes to integral of P dx plus Q dy plus R dz. Yeah. So this integration of function P with respect to x, and the integration of function Q with respect to y, function R with respect to G. So we can obtain this formula, right? So now, for example, we have an integration of this functions of this on C. So this is represented by F times dr, and here F is x and z and y and z and x. Yeah. Okay. So we finished section two này là hơi chậm trễ rồi, thầy đang dạy sang hiện tượng này là dạy sang section 3. Okay, let me see. Okay, fundamental. I take the so we study this section. The fundamental theorem for 9 integrals. So this is very important. Look back to the integration in calculus 1. We have a integral from a to b of derivatives of fx dx is exactly equal to fb minus fa. Is okay, right? Understand? Do you remember this formula? Còn nhớ cái tích phân này không? In case the function f it's exactly the derivatives of f, then this will become to fb minus fa. So that is the idea of based on the idea of integration in calculus 1. And similarly, we think of if f is the instead of replaced by gradient vector f. Okay, gradient vector f. Then we also obtain the similar formula. Nó không có cái tích phân của một cái đạo hàm, cái này là nguyên hàm rồi thì được lấy cái này. All right. So now we have theorems. Let's see the smooth curves given by a vector function r t. Here t on this interval. Now, if f is a differentiable function of 2 or 3 variables, with the gradient vectors f like this, then if we take the integration of f, integration of gradient vector f, then we have a f rb minus f ra. So now hello. Okay, so now you can see if f is we have this formula. So now if the function f, if the vector field f is a conservative, so it means that there exists the potential f such as f is gradient of f. Okay, then this become to integral c f f dr. So this is you can see this is equal to f rb minus f f ra. Understand? So you can see this is quite similar to this formula. So in special case, and we obtain this formula. Remember this when f is one variables, the function of one variables, and gradient f exactly is equal to f prime x. Okay, and r now becomes to dx. So we obtain this formula. All right. So now an example, we have works done by the gravitational fields f is like this. Okay, so it's moving a particular mass m from this point to this point along piecewise smooth curves, and we know that's because f is a conservative, and then vector field f is conservative. Therefore, there exists a function f such as vector field f is a gradient of f, and here f is like this. Therefore, dark news is integration of vector field f like this. And then, because we know f here, and then you can find the results. It's like this, very easy to calculate by using this formula. Yeah, using this formula. Right. Now, independent. This concept is a very interesting, very important. Independent part. So now, suppose that we have a C1, C2 are two piecewise smooth curves. Then we have the same initial point A, initial point A and terminal B in here. It look like this. The curve C here is divided to two parts, A and B. Here is C1, and here is C2. So you can see that the C equal to C1 union C2 has the same initial point A and B. The curve C1 and C2. Oh, all right. So now in general, the integral of f on C1 and integral f on C2 is just difference. In general, is difference. However, now when f is conservative, it means that f is the gradient of vector f. Then in this case, we have a integral C1 and C2 is the same, because this is equal to f of RB, okay, minus f of RA. Because we have a when t equal to a, small a, and t equal to small a, then we get the initial point A. When t equal to b, and we get the initial point B. Therefore, our integral on C1 and C2 is same. So remember this especially. In general, we don't have this. We don't have the equality here. All right. So now, in general, if f is a continuous vector field on the domain D, we say that's the integral CF is FDR is independent of a part if integral on C1 and C2 and same for any two parts C1 and C2 in D. Okay, so with this terminology, we can say that integrals of conservative vector field are independent apart. So as I explained before, right? Now, if our integral f dr is an independent part in D and C is any closed part in D, so we can choose any point. We can choose any point. And because it's independent, it does not depend on the initial and terminal points A and B. We can take A here and divide B here, and it doesn't matter. Okay, understand? So here, if you choose here, is a C1 prime and C2 prime. In case f is conservative or this independent parts, then integral on C1 prime and C2 prime same, or C1 and C2 same. Okay, so that is the idea. So now, because it's the integral CF dr equal to C1 plus the C2, And this is when we change the direction. We change the direction, then we get this is become to minus, near minus. So therefore, because it's the C1 and minus C2 has the same terminal point. So this is you see this is equal to 0. So now conversely, if it's true, so it means that the integral of f vector field f, so dr is equal to 0 whenever C is a closed part on D. Remember, C should be a closed part on D. Then we can conclude that this is the independent part. Okay. So now we have a theorem. The integral of f dr is an independent part in D if and only if C is equal to 0 for every closed path C in D. Okay. Understand? Nếu mà chúng ta có cái tích phân này bằng 0 thì ta nói rằng là cái tích phân này nó không phụ thuộc vào cái path on D, tức là tôi lấy bất kỳ cái path nào trong D thì nó bằng 0. Thì tích phân trên cái miền C1 với cái miền C2 với cái đường cong C2 là the same. Okay. All right. And how many? Nhiều quá nhỉ. Thôi cái này để buổi sau ta học tiếp nha. Bởi vì nó nhiều quá nên thử nói hết giờ nói nhanh quá thì nó không. Alright. So I think we should stop here. Chúng ta chỉ còn có 2 buổi nữa thôi, nên là chúng ta và cái thời lượng này cũng còn tương đối là dài đấy. Và thì các em biết lịch thi rồi đúng không? Chúng ta rất là gấp là học thứ 7 xong, thứ hai chúng ta có cái final luôn. Cho nên ngay từ đầu thầy đã nhắc lại cho thầy cung cấp cho các em đầy đủ các cái tài liệu. Bây giờ chỉ còn có phụ thuộc vào các em thôi. Bởi vì trên lớp các bài tập thầy cho trên lớp không thể các em biết rồi, là tuần nào chúng ta cũng có bài tập và chúng ta cũng có cái học xong lý thuyết chúng ta có bài tập luôn để thực hành và thầy giải. Nhưng mà số lượng cái giờ bài tập chúng ta không thể có nhiều được. Bởi vì nếu mà chúng ta lấy cái thời lượng bài tập nhiều lên thì sẽ không học kịp cái chương trình này, mà lúc bây giờ thầy giảng nó sẽ không có giảng kỹ được. Thực ra là chúng ta chỉ có một số lượng cái bài tập ở đó thôi, có thể các em hiểu ngay được lý thuyết. Còn chính vẫn là các em phải tự học, tự đọc cái tài liệu 5 bài tập. Tài liệu của các cái chương này thì thầy đã gửi rồi. Okay. Ngoài ra open math để chúng ta thực hành. Và thêm cái nữa là cái trang này là một cái trang thầy recommend cái trang này, một cái trang rất là hữu ích và nó có sẵn cả các bài tập, mẫu, lời giải, có video để các em xem. Recommend you follow this website. Người ta còn có cái video, thay vì các em nghe thì thầy giảng một lần cái lớp chưa hiểu thì các em, người ta có ví dụ, người ta có cái video, người ta tính từng step để giải thích cho người ta. Thầy không có thể có nhiều cái tài liệu hơn được nữa. thế này là thầy nghĩ rằng là nó quá đủ rồi, bây giờ nó sẽ còn chỉ phụ thuộc vào việc là các em có học hay không. Còn tất cả cái tài liệu thầy cung cấp có thể nói là rất chi tiết và đầy đủ, không thể đầy đủ hơn được nữa, đúng không? Các em có cái bài tập hàng tuần trên lớp, rồi thầy giải chi tiết. Ngoài ra còn có các cái tài liệu phụ thêm nữa, đọc thêm, làm bài tập. Và nên nhớ rằng là học xong thì phải làm bài tập luôn, làm càng nhiều càng tốt, từ các nguồn khác nhau. Đó, xem lại ví dụ các cái nguồn này, xem lại một lần để người ta giải thích qua các cái ví dụ, đọc cái solution ở đây thì để mình hiểu thêm. Các em phải hết sức cố gắng trong cái đạo chuyện đó thì mới có thể đạt được cái điểm tốt được, đúng không? Cũng không còn nhiều thời gian nữa đâu. Okay, any question? Thậm chí trong đây cũng còn họ có cả cái solution, đúng không? Nhá, để về nhà phải xem lại hết cái trang này, là cái trang nó rất là tốt, có cả video để người ta giới thiệu từng cái giải thích từng cái ví dụ để cho chúng ta hiểu. Rồi cái lý thuyết họ viết trong này cũng rất là xúc tích. Rồi ok, thế nhá. Có câu hỏi gì nữa không? Alright. Rồi nếu mà em không có câu hỏi gì nữa thì thầy bye bye các em nhé. Nhớ là làm bài tập các thứ đầy đủ, rồi học thêm qua các cái tài liệu thầy gửi. No. Alright. So bye bye các em.
Dạ, em chào.
Yeah.